Hi, I'm Oliver Choy. I'm from the Chinese University of Hong Kong. I'm going to talk about embedded system design training, a review. So here it goes. Why are we still talking about embedded systems? After all, they have been around for a long, long time. Here is the chip image of the very first processor from Intel, the 4004. Many of you probably know that one of the first main applications of 4004 is the calculator shown here. This is, of course, an embedded system. People usually associate processors with computers and servers. But the fact is, the majority of the processors are used in embedded system. Nearly 90% of them are shown in this graph. Even though this graph is almost 20 years old, I can assure you that this trend remains true as of today. And we can foresee that the number of processors demanded by embedded system will be rising. That is to do with two emerging devices, IoT devices, edge computing devices. You will agree they are, they are in fact embedded systems essentially. These two graphs show the rising market value for the two devices all the way to 2025, and the rise is accelerating beyond 2020. There are going to be a lot more embedded systems to design that gives rise to the need of a lot of more engineers having the knowledge and skill to design embedded systems. However, are we prepared for this upward trend? Are we training sufficient numbers of engineers? Are we offering them the right training? Many concerns, but I'm going to focus on training. It is an experience I had that inspires me to look into this question. I was helping a company to trace and solve problems with one of its embedded systems. One of the problem is the real-time clock, which does not function. At first, this seems to be an initialization problem, so I looked through the boot up routine, the software that runs before the firmware. I need to understand the boot up mechanism in order to locate the problem, but no luck. Then I looked back at hardware, and it happened that the problem was related to a reset signal, which was not properly timed. You will agree, in order to solve this problem, one needs to know how hardware and software work together in an embedded system. And another problem is the timer function. The system is supposed to turn off according to a set time. Strangely, the system did not turn off at the expected time occasionally. To locate the source of this problem was even more difficult. There were simply a lot of codes and programs interact with each other. It was further complicated by the fact that the system can also be controlled through the web. That means manual control and web control need to be synchronized. The problem was eventually solved after some efforts. My point is, this experience made me appreciate how complex an apparently simple embedded system can be. It is not just a circuit board containing a processor. And this also lets me wonder if we are training engineers to handle such complexity that has so many interacting components. Let us look into an embedded system in a bit more details. An embedded system, of course, is made up of hardware and software. Core of the hardware is, of course, the processor, but there can also be FPGA to implement random logic and accelerating signal processing algorithms. As I have highlighted, things can be even more complex on the software side. There are three programming domains one can find in the software, or normally called the firmware: machine level, kernel level, and application level. I'd like to look deeper into each one. At the machine level, one needs to know about assembly language in order to develop drivers, interrupts, in order to interact with hardware. Then, the core system function is normally implemented in C, which is executed with or without a kernel. The former is normally a preferred choice with good reason, as we can see in the next slide. With a kernel, you are provided with not only a file system, but interface to communication channels as well. And it also comes with many useful function calls like alarm and signaling. In order to make use of a kernel like Linux, one has to know about script programming, appreciate how multi-processes and multi-threads are working together, and other features like software interrupt and shared memory. At the application domain, the language used can be C or C++ or other high-level languages. Typically, if you are dealing with web control, one needs to know HTML programming using Java or Apache. Then there are Perl and Python, more modern-day programming languages to struggle with. With the different languages, one can do web HTML programming, client-server programming, and CGI, the Common Gateway Interface programming, for more interactive web page. I hope you will agree that an embedded system can be really complex, and that requires a lot of different knowledge and methodology to make the system work. I'd like to summarize in this list here. For hardware, one needs to know how to use processor, know how to design circuits, and implement them in FPGA. For software, the list of things to learn is much longer. Assembly language, hardware driver, implementation, and software interrupt, multiprocessing and scheduling, multi-threading and shared memory, script programming, network programming, client-server programming, web page development, CGI programming. The last but not least, understand the issues of protection, security, and encryption. And one needs to know how to make all these components working together, as processes and threads need to communicate with each other. Control, either through hardware or software, are required to be synchronized. This can be realized through things like global variables, share memories, share files, and perhaps other methods too. Now the question is, are we helping students to pick up all these knowledges and skills? I have looked into a few computer engineering programs offered in different institutions. I'm happy to report that all the programs I looked at include courses that are essential for embedded system design. Thing is, a typical computer engineering program is supposed to cover a much wider scope of training, not necessarily embedded system design. Only a few programs offer special streaming specifically tailored for nurturing embedded system designers. I'm dare to say the CE program in CUHK is one of them. Apart from general computing program and digital design courses common to all CE programs, the embedded stream offered by CUHK has three core courses on embedded system designs. The fundamentals of embedded systems give students the overall view of an embedded system. It even covers engineering drawings and the use of sensors. Embedded system design gives students the real deal. It covers the methods and skills to develop an embedded systems and how to use peripherals like serial and parallel communication channels, A to D, and how to interface to hardware on the one side and to high-level language on the other side. Embedded system development and applications covers advanced topics like real-time operating systems, interaction and interfacing to sensors and actuators. The emphasis is on the integration of different components. I'm glad to say project management is covered too. However, I still find all the courses related to embedded system design are taught in isolation. There is no coherence in delivering the courses, particularly those that cover the different programming domains, machine level, kernel level, and application level. What I like to advocate is a structured curriculum to train embedded system design engineers. The objectives are simple. Subjects should not be taught in isolation. The language in an embedded system needs to be emphasized. The students should be trained to have a comprehensive knowledge, skill, and method to put together an embedded system. It is important that the students should appreciate how the different components in an embedded system work together. Here is a rough skeleton of an embedded system design curriculum. The specialization in embedded system design should be introduced as soon as possible in the students' senior years. In the penultimate year, I suggest all necessary hardware-related subjects should be covered. C programming and kernel-level programming, like script programming, should be covered as well. In the graduation year, programming courses on web design, client-server model, CGI programming should be covered. A course on protection, security, and encryption should be offered too. But where can students can learn how an embedded system works? The best way to do this is through hands-on exercise with a project. Of course, the project should be embedded system design in nature. Such a project should cover the span of the senior years. Just like curriculum design, the project should also be well structured. I will use the development of a smart plug as an example. In the first project year, the students should complete the hardware construction, including circuit design, and implement a firmware which realizes the basic functions. In the example, this may mean simple on-off control. Then, in the second year, control through the web and some extended functions should be realized. In the example, this may mean timer control, on-off schedule, protection from hackers, and other safety measures. In conclusion, what I have suggested is admittedly very primitive. However, given the fact that embedded systems will become even more proliferated and conspicuous in our daily life, it is time to overhaul the curriculum and to ensure students are trained with the skills required by the industry. Hopefully, this can also address the wider issue of declining interest in engineering. Thank you.